Is this live? Are we good to go?
Yeah.
All right. Hello, everyone. My name is Nick Ingravallo, and I just put some slides together for my IDP9 submission investigating performance bottlenecks in the Plan 9 SPI driver. So I'll do the standard introduction. I'm a computer science major at Drexel, currently a senior. I got involved with Plan 9 through Professor Brian Stewart. I'd always liked OS work. I used to do some iOS jailbreaking stuff, some anti-cheat work for one of the games on the App Store, which I could talk about when this isn't live. And then I did some ENIAC research in summer of 2022 through a research program with Drexel, and I also did that with Professor Stewart. And it was about a instruction set that was theorized, well, what we know is an instruction set for the ENIAC, and it laid a lot of groundwork for a lot of modern computing, and it was a fun time. And I'd gotten involved with all of this. He'd showed me the simulator, and this is what it looks like right here. So you have all the accumulators on each of the sides. You can see this running in real time, and this is what I performed that research on. This all links to Plan 9, I promise. So this is how it all got involved with Plan 9. So I'd emailed Professor Stewart around this time last year, and I said, do you have any operating systems research? It's been a while since I was involved in it. And he said he had some Plan 9 related work because of the ENIAC simulator, which was running on Plan 9 through this LED matrix. So if I go back with all these accumulators, it was connected to this LED board, and you could select a specific accumulator which showed all the calculations, and it would show it live on this board. And it worked well, but if you did anything with the operating system, like you shook the mouse or you were typing something, there was this very clear stuttering that was going on, and it made it difficult to do things on the laptop and also show other people. It was very disruptive. So one of the things that we asked is there some kind of issue within the real-time scheduler? So this summer research term was born, and we called it Investigation into Real-Time Scheduling. So we had to do a few things in order to test the real-time scheduler because that's what we thought the culprit was. So I bought a Raspberry Pi 4, obviously the prerequisite, which, to note, is a multi-core machine, obviously runs Plan 9. And what we wanted to do is to simulate the system load that was taken by the ENIAC simulator. We just put a while one loop, pinned it to every single core, and we ran a real-time loop that ran at 1 millisecond frequency 30,000 times to test that if we're going around, we're doing other things with the OS, like the simulated load, it would take longer than the 30 seconds that we anticipated. So this is some of the code. Won't bore you with all the details of this, but it's literally just a while loop that you're running 30,000 times. Or sorry, a for loop that you're running 30,000 times. So it ran pretty much exactly as we expected. This 1 millisecond loop, 30,000 times, 30 seconds, a little bit of change in there just for starting the program and various other things. So we also tried it on the other cores. So cores 1, it worked well. Cores 2 and 3, it also worked well. So you're probably thinking, okay, well, what does this mean? This works exactly as you expected. And, well, I guess that's a good thing. Real-time scheduler when Plan 9 worked, and everything seemed to be going well in terms of that. The bad news is that there was still this flashing within this LED board that we didn't really know the root cause of. So we had to do a few extra steps to find the root issue behind this flashing in the ENIAC simulator. And one of the things that Professor Stewart had mentioned is that the ENIAC simulator engages with the GPIO driver and the SPI driver. This is for various things like selecting an accumulator and just anything related to displaying things on the LED board and controlling it. So one of the things we said is, well, maybe there's a failure in one of the drivers and there's some kind of issue going on that's causing it to slow down whenever there's system load. So one of the things we did is we wrote some C code in order to test this. So basically, I just took that for loop from before, and I put in a bunch of GPIO writes and a SPI write right before that 1 millisecond loop. So we know that under system load, this should run in 30 seconds. If we add this extra load beforehand, well, if it takes any longer, we know that one of the things going on here would fail. So I just wrote some example data, like the set 25 to the GPIO is for the LED matrix code, and the SPI data, we're just writing hex 41 8 bytes of hex 41 every 1 millisecond. We're trying to see if there's any kind of slowdown. So we ran it on core 0, and once again, it ran in 30 seconds. So we're like, all right, well, great. So we still don't know the issue. We ran it on core 1, and it ran in 70 seconds. So obviously, a lot slower. And then we repeated the test on cores 2 and 3, and it also ran in around 70 seconds. So if we look at the results here, either the SPI driver, the GPIO driver, some kind of combination of both, cosmic ray, I don't know, something was causing to cause this delay. So we had to go and we had to test all 3 of these scenarios. I'm not going to go through and show you, we replaced this code with this. I'll just tell you, it was the SPI driver. I'll save you all the time here. So what we did is we took that code from before, we ripped out the GPIO, and we just had the SPI write. So we're now writing, once again, hex 41, 8 bytes of it every 1 millisecond to the SPI driver, and we're just going and trying it on every single core. And with that alone, the results show that, yes, that was the actual issue. GPI worked fine, the real-time scheduler worked fine, but it was actually an issue within the SPI driver. So we had to go in and we had to see what the actual issue is and see if there's some kind of way that we can go and fix this. So if we look at the SPI driver code, we can see that the SPI read-write utilizes the direct memory access controller, the DMA controller, and within this, the SPI read-write function, DMA start is called twice and DMA wait is called once. So there seems that there's some kind of overhead there, and one of the things that we asked, is there a faster solution? Is there something that we can do besides this? So this is the code just to prove that it exists. SPI read-write function. Once again, not going to make you all read that. Just proving there's a DMA start, DMA wait, and there's also a cache invalidate, which probably doesn't help. So obviously we asked, is there any faster solution? So direct memory polling may be faster, where we literally just write to the SPI, wait for it to transfer, and wait till we receive kind of an OK back, which, although it might be faster than DMA, where there's no initialization, it's not concurrent. So this is something where we're like, okay, well, let's just see what happens. Is this any faster? Will this fix the issues? Will it be at least somewhat better in a multi-core environment? So this is some of the code, and I have this in the paper, which I'll link later. We just took the DMA code out. We literally, in the for loop for all of the data, write directly to the SPI port register. We wait for it to be transferred, and then we continue going. It is blocked in the kernel, but it seems to be a lot faster. So we ran the SPI loop again, writing 8 bytes at a time in a 1 millisecond loop, and this is the results compared to DMA. I know that was misleading. That's not the new results. So this is the old one. So core 0 ran in 30 seconds. It would be bad if it ran any slower. And then on cores 1 through 3, seems like we fixed the issue. So it now runs in the time that we anticipated, 30 seconds flat, and it had fixed this performance issue. So there was also some hidden advantages that I noticed, and this was just kind of playing around with it. We can actually transfer more data with the direct polling compared to the direct memory access implementation, where if we are in a real-time environment, like once every 1 millisecond, we can transfer at max hex 24 bytes with DMA, but if we're using polling, we can transfer actually around 75% more hex 40 bytes. So after that, it pretty much drops off. The kernel can no longer keep up, and everything just kind of breaks. But it is a noticeable increase, so it is pretty nice. And yeah, basically what I said, 75% increase. So we went through all of this. There were still a couple of weeks left in the term, and one of the things that we said is, well, why is this working better? So we know that this is a better solution, but wanted to get to the root cause of why the other DMA implementation was failing. So Yeah. Why was it much slower? So one of the things we went into is looked into system interrupts, and we saw that core 0 is assigned all of the peripheral interrupts. So this is anything with interrupt request number greater than 32, and all non-zero cores are assigned all the interprocessor interrupts, which are with interrupt request number less than, well, 32. So this is proving it right here. If the machine number of the core is 0, we get pretty much all of the interrupts. All the other ones are put onto cores 1 through 3, and from my understanding, it is selected as it's needed. So the DMA interrupts are handled with request numbers greater than 96. And when I looked into it, anything with request number greater than 96 is considered a global interrupt. And obviously, since this 96 interrupt is greater than 0, it's handled on core 0. Or sorry, greater than 32, it's handled on core 0. So from this, we now know that if we start the DMA start the program that we were testing with on core 1, and we initialize everything, DMA is initialized on core 1, no matter what happens, the DMA interrupts are handled on core 0. This is with the old implementation, and there's going to be some kind of cross-core latency that you have to deal with here. So obviously, it's required on every single call. So the polling solution was much, much faster than this, where we no longer have to go across the cores. If you start something on core 1, if you're just not dealing with DMA, you don't have to deal with this jump from core 1 to core 0. The concurrency benefits that we had were negated by the slow interrupts. So although it is technically not done in parallel anymore, it doesn't really matter, and it seems to be just as fast, if not faster, in some situations. And the last thing is there was just no performance degradation across the operating system. We were using this for a couple of weeks as we were finishing up, and we didn't notice any issues. So it seemed to have worked well. So clearly, this seems like the ideal patch. That's all. We're done. Yeah, that's never how it works. So there was one kind of idea I had, and this was actually completely after this whole research thing was done. It was something I had done as I was writing the paper. I was wondering if we could get around this cross-core interrupt, where if we leave the SPI code completely untouched, can we use the DMA implementation, start on core 1, and handle the interrupts, well, properly? So what I had done is I had found this function within the trap4.c implementation. So it is called interrupt2. And we can reroute any interrupt in the operating system to a specific core. So one of the nice things about the DMA is that if we actually have this, we can reroute it to the caller's core because we have all the information that we need here. We have the core number, we have the interrupt request number, and basically everything that we'd need. So if we go into the DMA code, this DMA start function, we can put a interrupt2 with the specific caller's core, the interrupt request number, and it'll reroute it to that core. So if we start this program on core 2, we can reroute the DMA interrupts to core 2, and pretty much any of the other cores. And it seemed like a very invasive change. Obviously, this is just the interrupt2 function. And there was no performance degradation when we ended up reporting it. The SPI code was completely untouched, and the rest of the system performed pretty much identically in preliminary testing. This seems like it works very well. We obviously know this is much more invasive. We're touching the DMA, which is much more widely used than the SPI code. However, it is an alternative, and it was something that we just figured was worth proposing. So that is all. This is a lot of fun, and thank you to everyone. If you want to see the original paper that I wrote, I put a QR code up on the screen. That is my link to the website, and if you want to ask me any questions or yell at me, tell me it's wrong, or any of that, here's my email. So that's all. Thank you all. I really appreciate it, and if you have any questions, let me know.
So two questions. So how big was the size of the buffer you were DMAing?
In the original code, I don't really remember.
It was 8 bytes, but I wasn't sure.
When we were testing, it was
Yeah.
8 bytes.
Yeah.
But we saw that it could go up to at least hex 24 before it completely broke. There was some work that if we set the real-time loop to sporadic, we could increase it, but just in a base environment, I think around 8 to 24 was where we kept it pretty much at all times.
And is there any, okay, because, I mean, generally, you know, interrupts in DMA engines aren't great for small things. That's why I was curious.
Mm-hmm.
It actually somehow is a winner, though, to use it for such small DMAs, or?
The interrupts being...
Yeah, you know, there's a certain overhead with an interrupt and with starting up the DMA engine and all that. So I was just wondering, and also the DMA engine itself in a lot of cases can be a single threaded resource. So if something else went into that DMA engine while you had something running, what happens there with the interrupt steering?
Honestly, I'm not entirely sure. It's been a while. We went the route of like replacing the DMA just because we found that there was a lot of that issue where there was the interrupts. It took so long to just get it started.
Yeah. Yeah.
So that we went away from that solution.
Yeah.
But that was the original one that we found like within the kernel, and I think that was cause of the bottlenecks. And we weren't aware that it was using DMA to start.
I see.
Which is why I think there were so many performance issues that we were just kind of unaware of, where we're just using it for the NEI simulator, but we're doing a DMA call every millisecond, which caused a decent amount of performance because of the overhead of just starting at the interrupts and everything in between.
Yeah, that's a terrific talk. Thank you.
Thank you. I appreciate it. And thank you for everything here. This is so much fun. It's great.
Was it Genesis that
Please, here. And queue up. Thank you.
So I'm not sure. Well, just keep
So you noticed no performance degradation using a polling approach as opposed to DMA. Did you measure power consumption at all, and did that make an effect? Because if there's no performance regression and power efficiency is about the same, then maybe it's just better to replace it with polling.
That's a really good idea. You know, we should. I'm not sure how we should test that. I do have my Pi 400, and I do have everything that I can do to like switch in between. I would love to test that and see. I mean, if that's the case, that'd be great, and that could be a good patch to implement. So yeah, I'll take a look.
These are nice.
Oh, you have one? Oh, nice. I may ask you to borrow that later.
This was a nice, sweet little talk. Thank you.
Thank you.
I'm curious kind of about your workflow on this. So you shared, some code that you had, which was kind of inspired. You had a hypothesis about how things were working. You probed it. Were there any more systematic ways that you went about trying to debug or troubleshoot this issue here, other than just like reading code and coming up with little tests yourself?
Most of it was based around that. Partially, I had gotten into Plan 9 literally the day that we started this. So there was there was learning all of it, learning the whole environment, and I mean, I was getting just used to the whole thing at once. So I hadn't had anything really complex where I just do, okay, well, if I measure this with a certain amount of time, I read the code, that is the bare minimum of debugging that I can really get. I think if I had a little bit more time, or I'd spent more time on learning, well, I spent as much time as I could learning the operating system, but if I had more context, I would have been able to do a more in-depth look, maybe just go into the kernel, see direct reporting. But for now, that's basically all I had, and just given the time constraints, we only really had 10 weeks. I felt that was like the fastest way to do it. But if I went in, saw it all, I'm sure I could have got to that conclusion faster or got a little bit more in depth than I had wanted to.
Right.
So,
Thank you, Nicholas.
Thank you.
We'll take that one first.
Well, I was just going to add a little something to that.
Yeah, just to follow up a little bit on that, we did look, we were prepared to, if we needed to hook up a scope to look at the pins and see what they were doing if the timing kinds of things weren't going to be enough resolution for what we did. But that turned out to be enough, and we didn't have to go any farther.
Okay, so actually, I guess 2 questions. One that's very related to the previous one, which is if we had some additional facilities in the kernel or in the system to debug this, what would those look like?
Ooh. I'm not sure if it's possible, but if there was way to directly debug the kernel and like measure things. I know like you have something like perf in Linux where you could write something, see directly how long it runs to get the performance metrics. That'd be great. And I'm not sure once again if it's available, but if you can add a debug statement where you trip a debug flag, you write it out, just some kind of very simple small metric to see how long things run within the kernel, that would be nice. Because I had found some like hacky solutions where I do like a print in the kernel. I'm like, this isn't great, and it goes to the output, and sometimes it completely bogs the operating system because the logging takes more time than what's actually being run. So if there were any performant ways to kind of debug it, or at least get some metrics out of it, if that doesn't exist, that would be ideal.
Okay, and I guess the other question is, you did a bunch of experimenting with routing the interrupt to the right core.
Yes.
With tiny messages on a specific SPI device, but you did a global change that affects everything. Did you measure the effects on, say, the disk driver or things that do larger?
Truthfully, I did not yet. I still have to. I was just using the operating system, and I had done my testing. And I was like, okay, this works well. I was doing that as I was writing the paper, and I was worried that I wouldn't have enough time. Just between that, other work, school. I wish I had more time too, but I didn't. I will be completely honest. However, I am graduating, so I do have some time, and I spent some time looking to Ninefront, the Adventures in Nine YouTube channel. I was looking into it all, and I would love to learn more about it. So, yeah.
So some of this code was written by Richard Miller, right?
Yes.
So did you ask him why he used DMA instead of direct polling, or if the size of the buffer was small, why not use direct polling instead of DMA? Did you ask him?
I have not. I think, Professor, if you want to say anything, but I personally had not, but I probably should. But we did correspond a bit with him about some Pi 5 work there.
Yeah, I should probably follow up on that. This is the code from Richard's port. The particular SPI code, however, is code that I gave to Richard that somebody else had started working with and said, hey, here's a starting point. I did a little work on it and then sent it to Richard, and that's how it got into that batch. As far as whether or not there was a lot of thought given to whether it should be polled or DMA. I believe, if I remember right, the original version that I got was using DMA, and I didn't really question changing it. It's been too long to remember for sure, however. But we have considered the possibility of maybe putting a threshold in there and saying, okay, for small enough things, do it polled, for larger things, do it DMA. There's a lot more kind of experimenting we'd like to do, like, for example, gauging what effect does this have on the disk driver and that kind of thing. So this is kind of our starting point, and there's definitely stuff that we would like to go farther with. Of course, how that plays into the Pi 5 port that just came out, we'll see.
I don't know if this is a question as much as maybe a suggestion, since I think the answer would probably be there wasn't enough time. But a interesting thing to consider for future work might be looking at some of the stuff that Linux has done with interrupt routing. So two things in particular: they do have a procfs that allows you to endpoint that allows you to associate an interrupt to a specific core, and there is a fair amount of performance-related work that's gone into when it's useful to do that for various kinds of interrupts. For example, if you have a core that's dedicated to some particular workload and it's heavy all the time, you don't necessarily want to throw interrupt handling at that core. On the other hand, it may be useful if the interrupt handling is related to that workload. So it might be something interesting to look at.
Thank you. Thank you. I will probably have some follow-up questions about that because I'd like to learn more, especially on the Linux side too. So thank you. I appreciate that.
I'm sorry, because this is actually, you're realizing this is a very important area to a lot of people. So I thought I'd mention, there was a 10,000 node Paragon system at Sandia back in the day. And every node had 2 Intel, Pentiums, right? And they discovered that the best way to run that in is you do the computations on the one Pentium, and the other Pentium just sits there and watches for packets coming in or out. No DMA, no interrupts, no nothing. And that thing just span on the ready. It would spin on the ready bits in the register, right? So they called that heater mode because the core doing the network got pretty hot. The other, I got to tell the ENIAC story, and I think we have a minute, right? When I was at Penn in the Moore School of Electrical Engineering, there are 3 or 4 ENIAC racks still left, and you could actually walk up to them and turn the dials and flip switches and stuff. And one day, somebody noticed there was like a rack missing, and so the hunt was on, and we ended up on the loading dock because there was a new guy in custodial, and he thought it was scrap. So
Oh my God.
they caught him as he was about to roll it off the loading dock into the dumpster. And so not long after that, the ENIAC was behind glass. You can still, when you get up there, if you get up there again, 34th and Walnut, you can go see it behind glass, or you used to be able to. But yeah, anyway, ENIAC almost vanished that little bit.
Oh my God.
Oh.
I'm glad you caught it. That's,
And the
that's
final
crazy.
ENIAC story, actually, they did find, my friend who was a professor at Penn did find all the documents at one point. They were in the basement of Moore School in the back, molding.
Wow.
So, it's just amazing how history can be lost. So I love your simulator. Anyway.
Looks like that's it. Then yeah, thank you again very much.
Thank you all.